Okay, it's start from current slide. Now, the only announcement I know about is the one concerning the Alabama A&M North Scholarship Program, and you got the email just like I did. You can check it out. They mention on there scholarship and internship program, but the student that was in one of my other classes said when he went to the site, he only saw the scholarship. So I don't know if he just didn't read far enough or deeply enough. I haven't been to the site. Most of the other programs have had an internship as well as scholarship, but I don't know. You can check it out if you're interested. All right, we're in Chapter 2, First Order Differential Equations, and 2.3 Linear Equations. And we finished Example 3, I believe, last time, and we're going to start on Example 4. Is that where y'all had us? Or did we get further than that? Because it's salt. I thought we... No. Okay, I think.
We hadn't started 3 yet.
We didn't? No, that was the one that... Oh, I was looking at the other one. That's the one that when you... The integrating factor was 10 to the minus 4, and... I mean, e to the minus... No, x to the minus 8. X to the minus 4, yeah. And it wiped out our x to the 5th. Didn't we do that? It's on page 58.
That's why.
Oh, okay. All right.
You're right.
Okay. Starting example 4.
Yeah.
Right. Okay. Got it. Okay. Found the general solution of this one. Whoa, let me get my pen set up. Okay. X squared minus 9 times dy dx, okay, plus xy equals 0. All right. Now, I'm pretty sure, just looking at this, without doing a great deal of work on it, yeah, I don't think you can separate variables. Well, maybe so. Wait, yeah, if you move that to the other side and multiply, yeah, I think you could separate variables. So I think this one could work with separation of variables, but they want us to use the linear form. Yeah. Now, before we begin, okay, notice this differential equation, and this is they're going to come up at the end, I think, on it. But when I see this, I immediately think one thing. Of course, what we're trying to do is find out the y that will make this true. When you take the derivative of blah, 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 you do this. You get a 0, right? That's what it appears to be, okay? However, when x is equal to plus 3 or minus 3, this whole term becomes 0, including your derivative. Your dy dx. So then you just have a situation of, okay, if x is plus or minus 3, then this x can't be plus or minus 3, but y could be 0 without the derivative, ever being, So this could have some singularities or some issues that may have solutions that you wouldn't think of. So when we're going to do this, we may or may not wind up with those solutions. If we don't, okay, but then we'll go back and say, or this could work too. But anytime you see something like this, especially when it's a homogeneous or homogeneous equation, then this can make this 0 no matter what this does. So this is taken out of the picture, and that's the whole picture. That's why we have the picture in the first place, doing the differential equation. If you lose the meaning of the derivative, then you kind of lost some of the meaning of the equation, or something like that. I don't know how to say it well, but that's the issue. Okay, so now they want us to do it using linear form. Is this in standard form for a linear equation? No, because it has this function of x in front. So how could we make it?
Number one, I would subtract x and y, and then I would divide by x squared.
Okay, all right. Okay, remember what our general equation for a linear equation looks like, general form for a linear equation. I'm going to go back to where they first talk about it. Okay?
General form, the standard form?
The standard form, that's the one I want.
Yes, page 55.
Huh? Yeah, it's equation 2 on page 55, right.
Okay,
And
so then all you have to do is divide by x squared
minus 9. Exactly. That's the first step. X squared minus 9. X squared minus 9. And I could divide this by x squared minus 9. Of course, that's still 0. Okay. So this goes away. Now in standard form, we have dy dx plus x over x squared minus 9 times y is equal to 0. Okay.
Why would it not be over x and y over?
Okay, you could, but what I'm doing is getting the, okay.
You're
if
right. You're right.
If you go back to that form, it's a p of x. And you want that to be a function of x. So we're trying to get the p of x together, and the f of x is 0. That's hunky-dory. But that step was illegal if x equal plus or minus 3, okay? Because then you divide it by 0. So again, this could be a possible sticking point here. We just have to keep that in mind, okay? But we really didn't want that to be plus or minus 3 anyway, so we're going to say x can't equal. In fact, I think I would say that at the very beginning here, comma, x cannot equal plus or minus 3, okay? And that'll take care of it. And if it is, we'll have to come back and take a look at it. All right, now, or at least on this step. Yeah, well, yeah, that's fine. Okay, now we have it in our standard form. And we've identified our p of x. What do we do with that p of x? Step 1 was get it in standard form. We just did. That implies identifying our p of x. Once we've identified it, what do we do with it?
Solve it.
Second?
You just solve it?
You integrate it.
Oh, no.
Okay? So we've got to integrate that. Let's come over here to the side and do that. The integral of x over x squared minus 9 dx. Now, how do we go about solving that? Anyone recall, remember what you have to do an integral like that? Oh, wait. I'm sorry. It's easier than I thought.
Yeah, just bring the denominator up to the top, -1.
Yeah, I guess that is a way to go. What I was more thinking is the numerator is the derivative of the denominator, isn't it? Sort of, close, within a factor of 2, right?
I don't understand.
Okay. On a problem like this, my process of internal process is how I do it. I look for the most complicated, troublesome part of that integrand. And what is it in this case?
X squared minus 9.
Exactly, in the denominator. Okay? Now I look at that and say, what can I do with it? But at first I was thinking, let's do partial fractions. That was the first thing that came to mind because it's set up perfectly for it. But you really don't even need to, because think of the derivative of this is what?
X.
2x.
Yeah, 2x.
Okay? And that's almost what we got. 2x dx, in fact. And that's almost what we got in the numerator. If we just put a 2 here and 1/2 out here, we'd be in Fat City, right?
Yeah.
Okay, so let's do that. Okay? Now, the other way to do this is called substitution. So if you prefer doing let u equal x squared minus 9, you don't like doing that. Okay. Well, if you see, to make the derivative of the denominator, which is sort of the same thing you were saying, the numerator, the derivative of the denominator, let's multiply by 2, but if you do that, you have to multiply by 1/2. That's legal in most states, right? Okay. So, what you have now is the numerator. I'm so used to do it in terms of u's. You have, if the denominator was u, the numerator is du, right?
Yes.
Okay, so this would be 1/2 the integral of du over u. What's the antiderivative of that?
Natural log of u.
That's it, exactly. Okay, so this is 1/2 the natural log of u. But u was that denominator, so this is 1/2 the natural log of x squared minus 9. Okay, and in order to clean this up just a little, it doesn't look like it's cleaning it up, but it really is. Let's bring the 1/2 and make it the exponent. Remember, that's one of the rules of logarithms. A times the log of b is the same as the log of b raised to the a power. Okay, so this is the same as log of x squared minus 9 squared. No, to the 1/2 power, sorry, to the 1/2 power. I can't write. Okay, let me clean that up just a tad, maybe a whole lot, to the 1/2 power. Okay, in other words, square root of that. Okay, if I prefer an exponential form. So that's what your integral of p of x is log of x squared minus 9 to the 1/2 power. What do we do with that integral of p of x? What was our process here for linear? Raise e. Make that the exponent of e. So, and that's why I did this. So e to the this would then be e to the log of x squared minus 9 to the 1/2 power. And what's the e of a log or log of an e?
Log of e.
No, they undo each other, right?
Oh.
Logs undo each other. So this is left with just being x squared minus 9 to the 1/2 power. All right, that is your integrating factor. That is the e to the integral of p of x dx. That's your integrating factor. So that's the thing we multiply by both sides of the equation. Multiply this. Okay? We just divided it out and now almost multiplying it back, but not quite. It's the square root of that. So we're going to multiply this, and this will be x squared minus 9 to the 1/2 power. Okay, dy dx. This drives me nuts. Plus, now, okay, no, we got this thing here. We're multiplying it by, this by both sides. So this will be a x squared minus 9 to the 1/2 power times x over x squared minus 9, okay, times y. And that's equal to 0 times that, which is just 0. Okay. Now, this is the square root of this, right? That's the 1/2 power, so it's the square root. This is that to the first power, so you could actually divide this into this and get this to the 1/2 power down here. Okay? Yeah. Okay. Now, supposedly, once you do that, multiplying that integrating factor by everything on both sides, you are supposed to wind up with a perfect derivative here. D by dx of some perfect derivative. What is that perfect derivative of? It's the disintegrating factor times y. Okay? That's supposed to be it. So it's x squared minus 9 to the 1/2 power times y. Now, I don't trust that I've done all the steps right, so I always at this point go back and check. Okay? So if I take the derivative of this, that's a product. So it's this times the derivative of that. That term worked perfectly, right? Plus, that works well. This, yes, times the derivative of this. Well, what's the derivative of this? 1/2 x squared minus 9 to the minus 1/2 times 2x. The 1/2 and the 2 cancel out. You just left with x. Yes, perfect derivative of that. So this thing is equal to 0. Okay? Well, now I'm going to write that in differential form. D of x squared minus 9 to the 1/2 power y is equal to 0 dx. I say 0 dx and just write dx. There's something wrong here. Okay. Okay. 0 dx. Okay. And what we're going to do now is integrate both sides. We've been doing a lot of that lately, haven't we? Okay. Well, the integral of a perfect derivative is x squared minus 9 to the 1/2 times y is equal to, and the antiderivative of 0 is c, a constant. Okay. We'll put c. Okay. Now, to solve for y would equal to c over x squared minus 9 to the 1/2 power. And that's it. And obviously here in your answer, x can't be plus or minus 3, and it can't up there, it can't anywhere. So that's out of the picture. Okay? And that should be our solution. Let's see what they got. Y is equal to c over square root of x squared minus 9. I put it to the 1/2. They put it back in radical form. Not that it ever was in radical form, but, you know, square root of x squared plus 9. There's your general solution. Now.
I have a question.
Yes.
Okay, so we got this term.
Right.
Why did we bring it back into here? Because I thought we had taken this.
Right. Okay.
And why did we bring it back in?
Okay. Okay. This was our integrating factor. That was e to this. That's our integrating factor. What do we do with the integrating factor? You multiply by every term on both sides of the equation. Okay, that's where it came from. This came back in. Now, this, remember, was not to the 1/2 power. Mm-hmm. This was to the 1/2. That was to the 2/2, right? Mm-hmm. 1. So, divided that and got that to the 1/2 power. Now, and remember what I was saying about plus or minus 3? They're going to make something go to 0 sometime or another, okay? And so those are what we call singular points. They can't be in the problem because our very first step eliminated them from the possibility. And even looking at the first rendition before we divided by that, you saw that if they were 0, you lose all meaning of your derivative. So those become singular points. They are going to make a 0 sometime or another that isn't part of our differential equation because the derivative part, the differential part, they've wiped them out. Okay? So that's what they're saying here. Notice in that 3 and minus 3 are singular points of the equation, and that every function in the general solution is discontinuous at those points. On the other hand, x equals 0 is a singular point of the differential equation in example 3. It's the one we did last time. Because x equals 0, look up at example 3, x equals 0 will wipe out your derivative there too. I mean, make it meaningless because that would be 0. And then you'd have minus 4y is equal to 0, so y would have to be 0. So you wind up with a singular point there that you don't want to happen. That's not part of your differential equation, so to speak. But its general equation that we did last time is noteworthy in that every function in that one parameter family is continuous to x equals 0, defined on the interval that, not just 0 to infinity as stated in the solution. However, the family is defined there cannot be considered a general solution since that singular point still causes a problem. So that was a lot of blah, blah, blah for that. In other words, you have to exclude these points from your solution. And as soon as you see them happening, it's a good time to get rid of them so they don't come up and bite you where you don't want to be bitten. Okay. So, ready for example 5? All right. Example 5 is an initial value problem using the same type stuff. Here's our solution, our problem, dy dx plus y is equal to x. Okay? And their initial condition y at 0 is equal to 4. Okay? Just some old initial condition there. All right. Now, the sort of good news here is this problem's already in standard form. And believe it or not, as simple as it looks, this one can't be solved by separation of variables because of that plus y there. That's going to be what messes us up if we multiply both sides of the. I don't think it will work, but that's never mind. Let's do it. Solve it using linear form, or linear process. And what's the first thing we do? We get it in standard form. It's already there. So what's the next thing we do? Second? Yeah, you first got to figure out what you're going to integrate.
So we're going to integrate y.
Your p of x.
Yeah.
And what is your p of x? 1. Okay, I think I can even integrate that one. Integral of 1 dx would be x, exactly. And on this integral, never put a plus c in there. It's just getting the antiderivative. That's all we're doing. And then what do we do with that?
E.
Yeah, we e it, okay? We make that as the superscript for the e. So our integrating factor is e to the x. And then what do we do with e to the x?
Now, we substitute that.
Not substitute, multiply it by everything on both sides. That's the integrating factor. It's a factor. You factor it, multiply it by everything. So you get e to the x dy dx plus e to the x y equal x e to the x. Multiply it by everything. Now,
is that dy dx, or is that
e to the x dx? Yeah, I'm sorry. My pen doesn't always last as long as it should, and sometimes it does too much or too little. Okay. Now, at this point, we realize this is supposed to be, if we did everything right, that's supposed to be a perfect derivative. Okay? What would that be a perfect derivative of? Well, it's this function, the integrating factor, times your y. It's what it should be every time. Okay? So that should be e to the x y. Now, cynic that I am, I want to make sure it is, because I don't want to proceed any further if I made a dumb mistake sometime earlier. Okay, so here's what I'm going to do. Take a derivative of this as the first times the derivative of the second. Yes, 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 that's fine. Plus, good, the second times the root of the first. What's the root of e to the x? E to the x. Yes, that is a perfect derivative. So since this is a perfect derivative, what we'll do is write it in differential form, which is d of e to the xy is equal to x e to the x dx. Okay. And I can even integrate this one. That integral of a derivative, perfect derivative, is going to be whatever the inside is. So that gives me e to the xy is equal to, now we have to integrate the right-hand side. And unfortunately, that's not one that is direct, but it's fairly easy. It's a product, and when you see a product there, and one's not a derivative of the other, then we try integration by parts, okay? And remember the rule for that? Let u be the one that when you differentiate, it's going to get simpler. And let dv be the one when you integrate that, it doesn't get any more complicated. So here the u would be the x part, and dv equal to e to the x dx. Okay, you always have to have the d's with the d's. Okay, so you take the derivative of the first one, then du is equal to simply, if u is equal to x, du would be? Huh? Oh, okay, sorry.
Okay, I'm sorry, where were we?
Okay. If u is equal to x,
Yes.
then you take a derivative of that, du would be
dx.
Perfect. Okay. That part was done. Now, if dv is this, what we're going to do is integrate both of those. Okay. And that would give you v is equal to, what's the antiderivative of e to the x dx?
Yes.
E to the x. Perfect. Okay. Now, this integral here is then going to be, you take the u times v, and that's simply going to be x e to the x, right, minus the bottom line down here. Okay, that's how I do it. When I write it this way, it'll be the integral of e to the x dx. Here's your v, here's your du. And I even could do that one. What would that be? Yeah, this would be e to the x. I mean, goodness, wait. I know, wait. X e to the x from here, bringing this over, minus e to the x. Now, at this point or some point here, we need to put a plus c. Okay? And this always gets a little tricky when you have e's in here. So I'm going to put a plus c now. I may want to change that shortly. I probably will. In fact, since everything on both sides has an e to the x in it, I want to make this an e to the c. That's a constant, isn't it? Yeah. E to the c? Yeah, okay. So, the e to the xy, that was from the left-hand side, is equal to x e to the x minus e to the x plus e to the c. I hope I did that right. Well, if it doesn't, I'll go back and change it. Okay? Now, what I want to do is divide everything. I want to isolate my y now to get my general solution. So I'm going to divide by e to the x. Okay? Now, that goes out, that goes out, that goes out, and we'll leave that alone for right now. So what we have now is y is equal to x minus 1 plus I may want to rethink that. I think I'll like it more this way. CE to the minus X. I think I like it that way, okay. Let's see if that's what the book did. Yeah. So let's not make that a E to the C, let's just make it C. Like we had it originally. Just a C. Sorry. Easy for me to blot out. In fact, I can make it seem like it was never even there. Okay? See, it wasn't there. Yeah, I didn't have that there. It's C. CE to the X, which is CE to the minus X. Okay?
Yeah, see, that makes more sense to me there.
Yeah. Okay. So there is our solution. Okay? Oh, but we have a boundary value, I mean an initial value. So let's plug that in. When X is 0, Y is 4. So let's put a 4 here, and then everywhere we see an X, we'll put a 0. That'll be a 0. Then we'll have a minus 1 plus C e to the minus 0. Well, e to the 0 is?
0.
No, 1. Anything to the 0th power is 1. Even e. Right? 7 to the 0th power is 1. Anything to the 0th power is 1.
Oh,
yeah. Okay. So the e to the 0 is 1. So we have C, 4 is equal to 1, minus 1 plus C. Let's add 1 to both sides. You get C is equal to 5. So now we go back to our general solution and write it as Y is equal to X minus 1 plus 5e to the minus X. I can't get the pen to write. There it goes. Now it writes all over itself. So there's...
So after we got C equals 5, what are we doing now?
Okay. Then we go back and plug it in here. This is our general solution. Now that we know specifically which C we're going to use, we put that in there. Specific solution. Oh my goodness. Be still my heart. He's here. Pharrell is here. He really is. And it thundered. Okay.
It's a good thunder.
Oh, it is. Okay. I thought the world was coming to an end. He showed up today. Okay. All right. Y'all have entirely too much fun in there. Okay. Now that's a really ugly X because it wouldn't write, and I kept trying to get it to write, and then it all wrote. So let me clean that up as much as I can. E to the minus X. No! Okay. I heard on the weather coming in possible thunderstorms. I said, in February? Yeah, in February.
I've seen tornadoes in February.
Yeah, and this, well, if it wasn't raining so hard, I could say I could believe it today too, but let's not. Okay, so there's our solution for this specific boundary value situation. The C that we use is C is equal to 5. Now, they do in your book, they show this solution. And by the way, when X is going to infinity, e to the minus X will be 1 over e to the infinity. In other words, 1 over a very big number is going to 0. So you'd have a line that would be X minus 1. Okay? There it is. It's a line, slope of 1, but y-intercept is minus 1. So there is your sort of your asymptote for this. Everything's going to be heading that way. When C is positive, you're up here, and when C is negative, you're down here. C is equal to 0, you're right there, because when C is 0, this part 0, you're X minus 1. So everything's coalescing on that, especially in the long run, when X is very, very large, that's going to go to 0, and C is equal to 5 would be this one right here. Okay? The dark blue line right there. That's the one, this boundary problem, because at y is equal to 0, X equals 0, y is equal to 4, and see it crosses right up there at 4. Why they put the scale up here, I'm not sure. crosses the 40. So that kicks out and says, that's the curve we're going to use because that's the one that fits our boundary value. Okay? I'm sorry, I keep calling it boundary value, initial value. Okay. Good deal. Now, all that talking about in the long run for large values of x, that last term, whatever it is, c e to the minus x, that's for very large x's, that's going closer and closer to 0. So we call that a transient term because after a while it has no value. You know, it's going to 0. So the bulk of the weight is carried by x minus 1. Now, when c is very large, it takes longer for that to be our thing. Because you see, when c was a small number, you're way down here, you know. So the curves are more important. But then when, and you have to get way up there. But then when c is larger, it's still going to have meaning way out here. But at some point, it's all going to go to that line. And when c is negative, they're going to that line as well. Okay, but they're doing it from the bottom side. Okay. So that's called the transient term because in the long run, it loses its meaning. It's only important in certain values. And sometimes can be quite important, like those earlier ones. All right. I think we're ready for, okay. We're going to introduce something that, on the one hand, almost seems like it doesn't make a lot of sense, but I think there are circumstances where it does. It's called piecewise linear differential equations. Now we had piecewise defined functions back in algebra and stuff like this. Now we have piecewise linear differential equations. What do we mean by that? In the construction of mathematical models, especially in the biological sciences and engineering, it can happen that one or more coefficients in a differential equation is a piecewise defined function. One or more of the coefficients in a differential equation is a piecewise defined function. Well, usually when they say coefficient, I think a number, okay? Now they're talking coefficient as if it's a whole function. And this could be a piecewise function. I'm trying to think if I could even imagine a scenario where this might be the case. Let's take something like a diode, okay? A diode, if I'm remembering right, allows current to go in one direction but not in the other. Yep. Okay. So that might be a piecewise defined function. If somehow that was in on your differential equation, what you're trying to model there, then it's going to have one value if I is positive and a different value if I is negative. That would be a piecewise defined function that could be your coefficient of one of your derivative term. Okay? And that would be then a piecewise linear differential equation. F of x is piecewise continuous at on the interval 0 to infinity with a single jump discontinuity at x equal 1. The basic idea, blah, blah, blah. Let's just go on and do it. Sometimes our verbiage gets so involved, I get lost of what they're trying to say. So let's just go to it. dy dx is going to come back plus y is equal to f of x. Oh, nice. Okay. And initial condition y of 0 is equal to 0. But the f of x, now this time they say it can happen that one or more coefficients in the differential equation is a piecewise defined function. So they're even counting the function on the other side as being a coefficient. I don't usually think of that word, but they're saying anywhere, any of the functions that are there. If you had a function that was a coefficient for your dy dx, that could be piecewise. If you had a function for your y, that could be piecewise, or even the function on the other side of the equation could be piecewise. And that's what they're doing in this case, where f of x is 1 for x for 0 less than or equal to x is less than or equal to 1, and it's 0 everywhere else. X greater than 1. Notice it's not even defined when x is negative, okay? So we're not even talking about that. We're only dealing an interval from 0 to infinity. Where in reality, that turns out to be, we're really only considering 0 to 1, okay? Because the function is 0 on the other side. But that doesn't mean the differential equation won't be meaningful there. But the function isn't. Okay. Now, what this means is you've got two differential equations to solve. One for x 0 to 1 and one for x greater than 1. Okay? And that's exactly how you do it. Now, I think they're cheating like crazy here, but let me verify that before I do anything else. Maybe they're not. But I thought... No. Okay. So let's do both pieces. Let's do the first piece where it's 1, the second piece where it's 0. So dy dx plus y is equal to 1, and y of 0 is equal to 0. Now here's going to be a problem for us, I think. In the second piece, we can't use our initial condition, because the initial condition is only good for the first piece. You see? X can be 0 in the top part of the piecewise defined function. The top piece, it's not defined in the bottom piece, because x is always greater than 1 down there. So we'll worry about that when we get there, but just keep that in mind. This boundary condition only applies to the top piece. Okay? Now how do we proceed?
Well,
It's in standard form, so we don't have to change anything there.
P to the x.
So the p of x is equal to, oh, you already done it. P of x is equal to 1, so when you integrate that dx, you're integrating 1 dx, which would be just x. So p of x, you're absolutely right, is equal to x. Okay? Don't ever put a plus c with this one. Okay.
All right, so we integrated dx.
Oh. Okay, I thought you said that.
dx.
Okay, wait. Okay, I'm sorry. I was just trying to catch up to where you were, but... Okay. If p of x is equal to 1, the coefficient of y, then of p of x would be the integral of 1 dx. So it's just dx. So p of x would... I'm sorry. The integral of p of x dx is equal to x. Right? And then what do we do with that? Integral of p of x dx? You e it. Okay? So then your integrating factor will be e to the x. It's very similar to what we just did earlier. So this will be e to, and then you multiply it by everything on both sides. E to the x dy dx. Okay? Plus e to the x y is equal to e to the x. Okay, we didn't do one just like this, but it was close. Now we hope that this left-hand side is a perfect derivative. D by dx of something. And what it's a perfect derivative of, it should be your integrating factor, e to the x, times your variable or your function y. Let's see if that's true. I think we've already done this once today already. That would be the first times the root of the second. Yes, it is. plus, good, the second y times the root of the first, yes. Okay? Now, and that's equal to e to the x. Now we write that in differential form. I'm going to come up here and do it, I think. And that would be d of e to the xy is equal to e to the x dx. If my pen will ever catch up. Okay, there it is. And then we integrate both sides of this. And the integral of a perfect derivative is, what's the integrand? E to the xy. Okay? And then we integrate that, and that's simply e to the x plus c, right? Okay? Now do your divide everything by e to the x. Okay? Those go out, and you have y is equal to 1 plus c e to the minus x. Okay? That's your general form. Now we plug in our initial condition, y of 0 is equal to 0, so 0 is equal to 1 plus 1. Wait, 1 plus c, sorry. Whew. So c is equal to is negative 1. Perfect. So now our solution is y is equal to 1 minus e to the minus x. Okay.
Wait, where'd you write that?
Huh?
Oh, right there.
Yeah. Yeah, I plugged it into this. Y is equal to 1, and then c is minus 1, e to the minus x. Okay. Now, this one, y is equal to 1, is going to be your equilibrium solution because e to the minus x is going to be transient. Large enough x is y is going to be equal to 1. Okay. Now, but that's only good from x and y is not going. X is not going to get large enough because it's going to be confined to be between 0 and 1. So it's going to be between 1 and that's where it's going to start when y is equal to 0. And then it's going to be sort of a transient downward, okay, because you're subtracting from it e to the 1.1, 1.2, 1.3, up to e, which is actually will go negative on you. Wait, I'm sorry. It's 1 over e. Sorry, I should have said that. Not 1, yeah. From when x is equal to 0, I'm sorry, I said that completely wrong. When x is equal to 0, e to the 0 is 1, 1 minus 1 is 1. So it starts at 0, and then it goes up to, and when x is equal to 1, you've got a 1 minus 1 over e. And 1 over e is about 2.7, so this is close to 2/3. Approximately 2/3. It's going to be a curve that goes up to 2/3. Okay? Then it's taken over by your next part, and let's see what happens there. Okay. What can I erase? I don't know. Let me erase it all. Okay. Because otherwise we'll be piecemealing it to death. I think I've even got to erase that. And I'll erase this. I'll probably regret doing all this erasing because I'm going to have to go back and reinvent the wheel here, but I think it'll just be too confusing. How are we doing on time? Oh, good. Okay. This time our equation for x greater than 1 is going to be equal to 0. And again, your p of x is equal to 1. The integral of p of x dx is going to be the integral of 1 dx, but it's going to be x. Okay, and then you raise that to the e, and you still get an integrating factor of e to the x. Okay, you multiply everything on both sides by that, and you get e to the x dy dx plus e to the x y equals 0. Because no matter what you multiply by that, it's still going to be 0. And of course, this is still your perfect derivative of d by dx of e to the x times y. Go back and check it. Derivative of e to x, e to the x times derivative of y plus derivative of e to the x times y. Yes, that's perfect. And that's equal to 0, okay? And when you integrate both sides of that, or write it in differential form, d of e to the x times y, that'll come back, is equal to 0 dx. And when you integrate this and integrate that, this comes out e to the x, y, and this comes out simply a constant, right? Antiderivative of 0 is a constant. Yay? Okay. So, but now we don't have anything to plug in because this is only for x is greater. So what we're probably going to want to plug in there, in order for you to have some sense of continuity here, you probably want it to be what the value was. And now I'm really regretting that I erased too much. But remind me what my formula was for the top. Y is equal to 1 minus e to the minus x.
Yeah.
Okay. So at x equal 1, that's its value. So at x equal 1, y of 1 is going to be 1 minus 1 over e, right? And you can plug that in and see what it is. It's something about 0.6 something another. If you got a calculator. Yeah.
I do.
Okay.
We're looking for 1 minus
1 over e. 1 divided by e to the 1. Yeah.
6, 3, 2, 1.
Okay, yeah. Something a little less than 2/3, right. Okay. Hang on to that, because now I'm going to say y of 1. Well, we'll leave it like this, but this is approximately 0.631 or 21. What do you say?
3.
3.1?
321.
321. Okay, something like that. Okay. I'm going to make that my boundary condition x when x is 1. We know that's where it's going to end up when x equal 1. The first one is, so this may not be fun, fair to do, but anyway, coming on down here, y is equal to c e to the minus x. Okay? But we're going to put that under this condition. So y, okay, let's put 1, let's see what, okay. 1 minus e to the minus 1, I'll put it that way, is equal to when c e to the minus 1, when x is equal to 1. Okay? So let's multiply everything by e. And that will, e over e is just going to be 1. Right? So we wind up with c is equal to e minus 1. So now in this part, y is equal to e minus 1 e to the minus x. Okay. So you're in the first part, when 0 is less than or equal to x is less than or equal to 1, this is your function. And when this is your function when x is greater than 1. Okay. And we actually made it so they have to be at the same point. Now, what is this one doing? E minus 1 is that not quite the same thing. This is 0.27 something other. Yes. Yeah. Because, yeah. No, 1.27. 1.7 something another. Because E is 2.7 something. 2.71. Okay. So E minus 1 will be 1.7. Okay. So in the long run, this is going to taper out. So this is going to go to 0 in the long run. Of course it will. That's your coefficient in front. And that gives you the same value, I think. So anyway, let's see how they did it. Yeah, where is it? There it is. Yeah. Y of x, and they actually wrote it a little bit neater than I did. Y as function of x is equal to, piecewise defined, 1 minus e to the minus x for 0 less than or equal to x less than or equal to 1, and e minus 1 e to the minus x. My board collapses on me, and so it makes the lines go less than straight. Yuck! Okay. That minus sign started heading downhill. That's anytime x greater than 1. So there's our piecewise defined answer. Okay? And that's continuous on 0 to infinity. Not counting 0, but from 0 to infinity. Okay. Now, let me show you what this looks like. Like I said before, this function starts at 0 because your x is equal to 0, your y is 0. That's what your boundary condition says. So you're starting right here, and it's an exponential, it's an increase here anyway, in a weird kind of way, because it's e to the 1 minus e to the minus x. E to the minus x is this way, 1 minus that, yeah. So it starts off going like this, but then once it reaches 1, then it, because we want it to be continuous there, it starts approaching 0, and sure enough, I can't hold this up. That's what the function looks like. The derivative is undefined right there at that point because it changes its magnitude. It's sort of like a cusp, or not quite a corner. So the derivative is not defined there, but it's continuous. The function is continuous there, and that's what it looks like. So it can't just abruptly change everything. All right. Now they get to something that I don't know in what, but they say, they started out. In mathematics, science, and engineering, some important functions are defined in terms of non-elementary integrals. And we talked about some of these at the end of one of the sections earlier. Two such special functions are the error function and the complementary error function. Okay? And I'm just going to write down what these are. And we may do a little something with them, but they're not any of my favorites, because I've never really in my life that I can recall had any use to deal with either one of them. I've seen them, I've read about them, I've had to do problems with them, but I've never actually run into them. Now, maybe y'all do or will in your fields of study, but I've never run into it in mine. So, but I've always heard about it and had to deal with it. Here's how the error function is defined. The ERF of x. Error function of x, okay, I guess. ERF of x, okay, whatever you want to call it. Here is its definition. How have my watch covered here. See, we're going to, oh yeah, we got a little over 5 minutes. Okay, 2 over the square root of pi, one of my favorite numbers of all time. Integral 0 to x of e to the minus t squared dt. Now, let me take back something now that I'll think about this. This is really not too far from being your normal distribution curve, your bell-shaped curve. That's pretty close to what this is becoming. Okay? So I'll take it back. I have used it. You use it a lot. If you're using statistics, you're using it. Okay? Or something very close to it. But guess what? You never use this. You go use a table. You use a computer program. You know, you never do this. But this is how it's represented. Try solving that. Go to any table you want to try solving it. This is what they call a non-elementary integral. There is no solution to it except in a table or somewhere like that. Okay. Now, the complementary error function, which is the ERFC of x, it seems like they call it the surf, but they don't. They call it ERFC, okay, of x. And that starts the same way, 2 over pi. And then the integral is now x to infinity of e to the minus, same thing, e to the minus t squared dt. Okay. Only difference is you've changed your variable here. If you want to see what they're going to say next, proven, go to Appendix A. It says from the known result that the integral from 0 to infinity of e to the minus t squared dt, everybody's supposed to know this, is equal to the square root of pi over 2. Okay? All right. Everybody's supposed to know that, and I can't for the life of me remember why they're supposed to know it. But I guess they're supposed to know it. Okay?
Is it the error equation or the complementary error?
It's the combination of the two. If you go from 0 to infinity, which is taking the error function and adding to it the complementary error function, okay, then you get, but leaving off the coefficient in front, then you get this, okay? Now, and I can't remember why everybody's supposed to know that, okay? It says, from the known result that this is true, then you can write, if you divide both sides of this by, or multiply by 2 over root pi, then this becomes 1, and this becomes, well, let me multiply it by 2 over root pi, and multiply this by 2 over root pi. If I could write, this is equal to 1, and that would tell you that then if you add these two together, you get 1. Okay? Which, of course, is this thing down here. And that's why I say it's the normal curve, because the area under the normal curve is 1. Okay? Except that's not quite right, because this is only from 0 to pi. The area under a normal curve would be both sides, wouldn't it? Seems like it would have to be. But if you're only dealing with one side, then if everything's defined by this, the probability of it happening is going to be 1. And if it's happening from here to here, this is the probability would be between 0 and x, and then the probability that beyond x would be out there. So what you're doing with statistics a lot of time is saying that your null hypothesis, if that did, the likelihood of that being true is going to be this little piece out here, that under the tail, and that's going to be very, very small if your null hypothesis is to be rejected. And then, so you're going to accept that the alternative hypothesis is true, that this thing is having an effect. Blah, blah, blah. All right, okay. That's what statistics is all about, and that's why it's so much fun. Okay. Now, so this means that the error function plus the complementary error function always adds to 1. All right. Now,
would you always add?
What's that?
Would you always add an error function?
Well, I mean, this is just telling you what the complementary error function is. If the error function gives you some number, and guess what? It's always going to be something less than 1. Got to be, okay? So it's going to be some number, 0.725. Then the complementary error function is going to be 0.275. Okay? It's got to be because the two of them have to add to 1. If you're not under this half, you're under that half. And the total is 1. That's what this says. Okay? Because everybody knew that. You know, it's sort of like a Geico commercial or something like that. Okay. So if we're solving an initial value problem like number 6, okay, and recognize that the indefinite integral of the right-hand side, we're probably getting close to being out of time, aren't we? How much?
Yeah, 3 minutes.
3 minutes. We don't have time to do the problem. Let me read the thing. If you're solving an initial value problem like number 6, recognize that the indefinite integration on the right-hand side would lead to a non-elementary integral. Then, as we saw in example 5 of section 2.2, yeah, I remember that, it is convenient to use instead definite integration over an interval x0 to x. The last example illustrates that this procedure automatically incorporates the initial condition, blah, 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 blah. Okay. In other words, we do not have to solve for the constant c in the general solution. So we will start next time with the example 7, which will show us all that in no uncertain terms. And homework exercises here will include any of the odds 1 through 23. I assigned those last time that are in the back of the book, by the way. And any of the odds 25 to 35 that are in the back of the book. I assigned those last time. Either 37 or 39 if they're in the back of the book. There's the new ones. Those are the ones we did this time. Piecewise defined functions. Okay? And yeah, I think you can do number 40, another 41, that's if it's in the back of the book. And 43 if it's in the back of the book. And I think, well, no, forget 43 until we do the next example. Stop at 41. Okay. So we just added basically we did some other stuff too, but then added the piecewise defined functions right at the end. All right, good deal. And we will finish 2.3 next time, knock on wood, and move on to 2.4, which are fun, exact equations. And then, I just missed 2.5, which is substitutions, which are not quite as much fun, but they're okay. And then we'll touch on a numerical method, and that'll be it for chapter 2. So be working on 1, so we'll have that in before we do 2.
I'm still struggling with 1.